Welcome, everyone, and let's jump right into this explainer. Today, we're taking an engineering deep dive into what just might be the absolute greatest thermodynamic hack in history. For all you aspiring mechanical engineers tuning in, exploring this is a super fascinating way to see how looking at a fundamental physical problem from a totally different angle can, literally, change the world. We're going to deconstruct James Watt's separate condenser. It's the breakthrough that took the steam engine from a clunky, coal-guzzling mine pump and transformed it into the beating heart of the Industrial Revolution. But to really grasp the genius of Watt's invention, we first have to understand the massive brick wall that 18th century engineers were just banging their heads against. The fundamental paradox was this: how do you keep a cylinder simultaneously boiling hot and freezing cold? I mean, it sounds impossible, right? You know thermodynamics. You want your power cylinder as hot as possible to conserve thermal energy. But to create a vacuum using steam, you need it freezing cold to force condensation. Before Watt, engineers were forced into a compromise, and honestly, that compromise came at a massive, massive cost in fuel and efficiency. So, here's our roadmap for today. First, we'll cover the thermodynamic paradox. Next, we'll look at the mechanics of the condenser. Third, achieving the perfect seal. Fourth, expanding to rotary motion. And finally, the efficiency revolution. All right, let's kick things off with Section 1, the thermodynamic paradox. To appreciate the cure, we really have to examine the disease. So let's look at the fundamentally flawed predecessor to Watt's design. Introduced in 1712, the brute force Newcomen atmospheric engine was definitely a marvel for its time. I mean, it could replace a team of 500 horses pumping water out of deep coal mines. But consider how it actually worked. It created a vacuum by injecting a jet of cold water directly into the steam-filled power cylinder. The steam would condense, the pressure drops, and then the atmospheric pressure outside pushes the piston down. So it worked, but from a thermodynamic perspective, absolute nightmare. Think about it. The Newcomen cycle meant you had to constantly reheat this massive metal cylinder every single stroke, just because you sprayed cold water inside it. You were burning through literal mountains of coal just to bring the cylinder back up to steam temperature, wasting tremendous amounts of latent heat. But then, in 1765, while repairing a model Newcomen engine at the University of Glasgow, James Watt had a total revelation. What if you separate the heating and cooling entirely? Keep the main cylinder permanently hot and cool the steam somewhere else. Boom! That brilliant idea brings us right into Section 2, mechanics of the condenser. Because, as we all know, it's one thing to have a great theory, it's another entirely to engineer the actual hardware. Watt's solution was the separate condenser. He designed a completely separate chamber kept permanently cold in a water bath, and crucially, maintained below atmospheric pressure. This chamber was then connected to the main hot power cylinder by a simple valve. There's a great story where a friend visited him shortly after this breakthrough, and Watt was just staring at this little tin cistern in his parlor. He confidently announced he had made an engine that wouldn't waste a single particle of steam. Let's walk through these stroke cycle mechanics together, step by step. Step 1. Steam from the boiler fills the main power cylinder, which is kept piping hot by a steam jacket. Step 2. The piston hits the top, the steam inlet closes, and the valve to the condenser opens up. Step 3. Now, because the condenser is sitting at a lower pressure, the steam is literally drawn out of the hot cylinder and sucked into the cold condenser, where it instantly turns into liquid water. Step 4. This rapid phase change creates a vacuum, and the external atmospheric pressure just pushes the piston right down. The beauty of it? The cylinder stays hot, the condenser stays cold. The paradox is completely solved. Moving right along to Section 3, achieving the perfect seal. Because, let's be real, engineering is rarely that easy. Transitioning from a brilliant thermodynamic theory to a physical functioning machine was a brutal manufacturing hurdle. For all the aspiring engineers tuning in, burn this into your brain. A brilliant design on paper is absolutely useless if you can't physically build it. The old Newcomen engine, it didn't need a precision seal. Guys just left a pool of water sitting on top of the piston to plug the gaps. But Watt's engine needed the cylinder to stay at steam temperature. If he used water to seal it, the water cools the cylinder and completely ruins his efficiency gains. He needed a perfectly round cylinder to prevent steam leaks. And he struggled for years, simply because the tooling just wasn't there yet. To give you an idea of how tough this was, the prominent 18th century engineer John Smeaton reported to the Society of Engineers that neither the tools nor the workmen existed who could manufacture such a complex machine with sufficient precision. And Smeaton wasn't trying to insult Watt. He was just stating a harsh reality. The metallurgy and machining capabilities of the 1760s simply could not handle the incredibly tight tolerances required to make a piston perfectly flush against a giant iron cylinder. But then, enter John Wilkinson in 1774. This guy developed a brand new precision boring machine that was originally meant for making cannons. The genius here was that the cutting tool shaft was supported on both ends and extended all the way through the cylinder. This brilliantly stopped the cutting tool from vibrating and deflecting, resulting in beautifully accurate, consistent cylinder diameters. This perfectly bored iron cylinder was the exact missing piece of the puzzle that finally solved Watt's critical steam leak issue. Hardware development is an absolute marathon, guys. Look at this timeline. Watt had the idea in 1765. He got his patent in 1769, but it wasn't until Wilkinson's boring machine in 1774, plus the financial and operational backing of his new business partner, Matthew Boulton, that they could actually produce the thing. The commercial launch finally happened in 1776. That is 11 long years from the little tin cistern moment to a working commercial product. Never, ever underestimate how long hardware development takes.
Okay, let's dive into Section 4, expanding to rotary motion.
Solving those thermodynamic and manufacturing issues paved the way for something even bigger, fundamentally changing how mechanical work was applied to the physical world. For decades, steam engines were essentially just giant, linear, single-acting pumps pulling water out of deep mines. It was just a one-way tug. But Watt didn't stop at the condenser. He realized that if he closed the top of the cylinder and injected steam on both sides of the piston alternately, he could create a double-acting engine. It could push and pull. And if it could push and pull, it could be connected to a wheel to provide continuous, smooth rotary output. Game changer. But how do you connect a straight-moving piston to a spinning wheel? Well, Watt developed some frankly brilliant mechanical linkages to make it happen. First up, parallel motion, an elegant 4-bar linkage that kept the rigid piston rod perfectly straight while the heavy beam arced above it. Second, because a competitor actually held the patent for a simple crank, Watt used a sun and planet gear. This was an epicyclic gear system suggested by his employee William Murdoch, and it converted those up and down strokes into rotary spins. Finally, the centrifugal governor. Adapted from windmills, this ingenious device automatically throttled the steam intake to maintain a constant, steady engine speed regardless of the load. And that brings us to our final section, Section 5, the efficiency revolution. Let's look at the massive economic and industrial impact of these combined breakthroughs, because the numbers really don't lie. The old Newcomen engines hovered around a 6.4% theoretical efficiency, but Watt, by sealing the cylinder, adding that separate condenser, and implementing steam expansion, which is where he cut off the steam supply halfway through the stroke and let the pressure expand against the vacuum, jumped the efficiency to nearly 10.6%. Now, in the realm of mechanical engineering, achieving a 65% relative increase in your baseline efficiency, that is a monumental victory. But the metric that truly mattered to the factory bosses? A staggering 75% reduction in coal consumption. 75%! Because of Watt's thermodynamic hack, his engines required just a fraction of the coal to do the exact same amount of work as a Newcomen engine. In fact, Watt and his partner Boulton were so incredibly confident in this, they didn't even just sell the engines outright at first. Instead, they charged a licensing fee based specifically on a portion of the fuel costs that the customer saved. How's that for a business model? The ultimate consequence of this engineering was that the steam engine totally decoupled industry from geography. Think about it. Before Watt's rotative steam engine, if you wanted to build a mill or a factory, you had to build it right next to a river with a strong, reliable current to turn a water wheel. And if that river froze in the winter or dried up in the summer, your production completely stopped. Watt's engine meant you could put a factory anywhere. It sparked explosive global industrial growth, driving productivity, creating massive new job markets, and completely transforming global supply chains. Which leaves us with this final thought. James Watt looked at a machine that had been the undisputed industry standard for 50 years, noticed a glaring thermodynamic paradox, and fundamentally changed the architecture to fix it. So I leave you with this question. As we push the very limits of modern efficiency in our own work today, what is the next separate condenser waiting to be discovered in your field? Keep looking for those paradoxes, you guys, and keep engineering solutions. Thanks so much for joining me on this explainer, and I'll catch you in the next one.